uh, and we share your delight with all the contributions that other people have made to this. And just to kick off the discussion, perhaps I can put you on the spot, both of you. If there was one single thing that you would like solved, what would it be? Patricia, you want to go first?
That is putting me on the spot, isn't it? Well, the problem is everything depends on everything else, but the way things depend on metallicity in detail, if we began to understand that, and I have some hopes for that from the observational perspective, from the work Steve Goldberg described that's going on in M31 with Martha Boyer, of looking at AGB stars in clusters there. We will get metallicities from the clusters and we'll get properties from the AGB stars. And I think that may give us a start to understanding dependence of at least some things on metallicity. Let me go on thinking about this question while Philip has a go.
No, that's great, because that's where it starts. Once you have metallicities, then you can see how it affects all the other things, and perhaps then we can constrain theories. Philip.
So, well, I'm going to tell you, so I know exactly what my answer is, but no one else is going to like it because it's not really an important problem. But I think it's a really fun problem, and I think it's an interesting problem. And that question that I would like answered is, do TZOs actually exist? I was fortunate enough to be invited to this wonderful meeting that Emily Levesque put together last week at the AAS, where Kip Thorne gave the intro talk and Anna Zekov gave the closing talk. And I am, it's the main question was really in some ways never addressed. So all the theoreticians feel that Thorne-Zykov objects should exist, but we only have one, maybe 1.5 suggestions of ones. And they both fall in the same place in the color magnitude diagram. And they could very easily be super AGB stars. And how can you tell the difference between a super AGB star and the TZO star is an unresolved question. And I think it would be fun to answer that. I don't think it's the most pressing question in the field, but I think it would be one of the more fun ones to answer, whether these exotic objects, for those of you in the audience who have no idea what I'm talking about, the idea, Kip Thorne and Anna Zykov in the late 1960s, early 1970s, maybe I'm off by a decade, suggested that you have two stars, one way of doing it, two massive stars in orbit around each other. One of them evolves, the more massive one turns into a neutron star after it blows up, and the other one eventually expands into the red supergiant phase and engulfs the neutron star. And you now have a neutron star in the middle of a red supergiant masquerading as a red supergiant star, but producing all sorts of funky elements that nobody can pronounce or spell because of the nuclear reactions going on this incredibly hot layer at the top of the neutron star. And there's a candidate that's been proposed, and it's a good question. Anyway, that's what I would like to see answered.
Yeah, thanks, Philip. It's a very specific point. So, no, that might be a nut to crack, but then it might also be the hardest nut to crack, and we might still be here in another 20 years. We never know this.
Can I contribute to this?
Sure, go ahead.
I mean, I think that to some extent that brings us back to these very luminous, very thick dust shell sources, which have periods of 2,000-3,000 days, that we're starting to discover in other galaxies, because that would include candidates for TZO objects and super AGB stars. And we don't even begin to understand these, except for similarities to OHIR stars at the short period end. So that's perhaps we can help solve your problem and some of our AGB problems at the same time by looking at those stars in more detail.
Great.
Julia, you want to carry on this?
Sure, yes. Well, both great points. If anybody else want to, yes, I see somebody like Emily wants to say something. Please go ahead.
Hi, can you hear me now that I'm unmuted?
Yep.
Excellent. So I just expand on Phil's point, which I agree with. I think it's a really fun question. And the point that it's maybe not the most pressing question is fair, but I think that there's a lot of pressing questions that get answered along the way while studying TZOs. And Patricia just brought this up with the question of very strong mass loss and the puzzle of OHIR stars. We've seen some great talks this week on convection and what that does to the light curves of red supergiants, and knowing that we would need to be able to disentangle those effects before we can explain TZOs. So I think that it's a fun goal in that there's a lot of scientific questions that have to get tackled along the way. And a lot of the talks we've seen this week, period, and in particular, a lot of the talks trying to get to the bottom of these questions about red supergiants are questions we'll have to answer as part of this. So it's a nice catch-all topic. It has a quirky end goal, but to reach the end goal, it puts a lot of fundamental questions front and center.
Yeah. Yes, if Philip or Patricia wants to add something else, otherwise we can go on. Patricia, do you want to say something?
Not about this, about something else later.
Okay. So let me ask a couple of questions that have been brought up on Slack. Please feel free to post more, and Patricia, please hold your comments for later. So Marcelo say Philip made a very good point. This is something which is well known by stellar evolution modelers, but not usually discussed in papers or even in textbooks. The mixing length theory does not have only one free parameter. And Marcelo, do you want actually to continue on that yourself?
Okay, it was just sorry. It was really not a question. It was more of a comment only. That I mean, as you were already reading, I mean that the mixing length parameter, the mixing length does not have only one free parameter. The one we usually call the alpha mixing length. You know, the well-known free parameter. But in fact, when you divide the equations, you made a lot of assumptions, and then if you really put the free parameters that come with these assumptions, then you end up like with 4 or 5 free parameters. So the whole theory, in fact, has like 5 free parameters, more or less. I don't remember exactly the number. But then, of course, when you derive the equations, you fix them to given values, like 1/2 or something like this for most of them. And you end up with only 1 free parameter that you keep. And say, so in principle, depending on which equations you are following, in particular, which textbook or paper you are following to write down your mixing length equations, you have really chosen different free parameters. Then, of course, you cannot compare only the alpha parameter between different codes, because they involve also the other free parameters that you arbitrarily choose. So that's the only thing. And of course, the other thing is that when you calibrate the mixing length parameter, usually in a way, you incorporate all the uncertainties and differences in the microphysics and the macrophysics between your stellar evolution codes. And then, of course, you cannot compare one code with the other, at least not the alpha value directly.
All right, thanks for your comment. And unless anybody else wants to comment on this, there is Biwei who is asking Patricia, it seems to me that super AGB stars are located in the region of the TP AGBs in the J-K diagram. How to discriminate the two types in the CMD?
Yeah, the candidate super AGBs in the small Magellanic Cloud are somewhat more luminous than the hot bottom burning stars. I mean, then they're not third dredge up stars in that they're certainly more luminous than we see third dredge up in. they are comparable to the hot bottom burning stars, but I think the distinction is that they are more luminous, and where they're pulsating, the periods tend to be longer, which means that they're bigger stars, more extended. But that certainly doesn't give you the answer. I suspect the answer has to come in detailed abundance analysis, but then there needs to be detailed theoretical predictions that you could measure against.
All right, thanks. I see that Ben Davies is with their hand raised.
Hello, can you hear me?
Mhm.
Yeah, so I just had a comment, I guess, on, so Phil mentioned that using the luminosity functions to get at the mass loss rates for red supergiants. So I think in Catherine's paper, they explored high mass loss rates and that you can rule those out because of what it does to the luminosity function. But when you go to lower mass loss rates, it doesn't really make any difference anymore. It's basically off. And so turning the mass loss rates down by, say, a factor of 2 or 10, I don't think it makes any difference to the luminosity function. So I'm not sure that's going to help us figure out what the mass loss rates are if they're lower than they already currently are in the evolutionary models. And then the second point on this is from Sarah McDonald's contributed talk, that if you look at the luminosity functions in M31 and the LMC and the SMC, they're pretty much indistinguishable from each other. And that's really not what you expect at all from these same evolutionary models. So I think that comparing what we observe to the predictions of evolutionary models isn't really going to tell us much. I feel like the observations are informing the models rather than the other way around. Combined with the uncertainties on effective temperatures, I feel like evolutionary modelers are waiting for us to tell us what to reproduce.
Okay, thanks. And I see that Jaakko has a comment on this.
Yeah, well, to follow up on that, so I think there are two, or at least two things that are important that have been pointed out. The first one is about mass loss varies in time for a given star. And this is important both for when you try to measure mass loss rates in the field or in clusters, and for if you want to incorporate mass loss in your models. And so it's very important that modelers understand the biases in certain measurements of mass loss rates, and vice versa, that when we compare observations with models, that we understand how the mass loss is actually incorporated. And the second point is that mass loss rates cannot be determined very accurately. And so you can look at it in a statistical way, but you might still have systematic offsets. And for any given star, the uncertainties are very large. So it becomes very difficult to actually use the mass loss rates to constrain models. Ideally, we would understand physics and be able to reliably model and then compare that with observations, because I think observationally there will always be degeneracies and simply inaccuracies. And I don't think we will ever be able to determine the mass loss rate of, say, a red supergiant observationally to say 1% accurate. But maybe I'm wrong. Please prove me wrong.
Can I come back on that?
Yep, Ben has, yeah, please.
Yeah, so whilst I agree that there are errors on mass loss rate measurements, right? You shouldn't just give up just because you've got errors, right? You can measure your errors and you can estimate what your systematic errors, what you think they should be. You can also look at how far your mass loss rates need to move for it to substantially change your conclusions. And then you see if that's within your error budget, right? So from Emma's stuff, which is not the last word on any of this, right? Anyone could challenge this with a different mass loss rate measurement method. But from Emma's conclusions, what she said was that the mass loss rates are too low by a factor of 10 to 20 to 30. in terms of can the mass loss rates make red supergiants evolve back to become Wolf-Rayet stars? And so for mass loss rates to be important in terms of the evolution of red supergiants and their onward evolution to the blue, then her mass loss rates would have to be out by that much. That would be, that's well outside the error budget, right?
Yeah, I didn't mean to say that no, we should just stop measuring and give up. There are certainly constraints to be obtained, but if you have a certain margin of error and the models fit within that margin of error, that does not necessarily mean that the model is correct. This becomes philosophical, probably.
I don't see any more questions on Slack, but I actually do have a question for Phil. You mentioned you wanted to see more phonics modeling. Were you referring to red supergiants, or this is because we have actually started to try this for a set of K giants. What we have been trying to do is to model these. Those are data that come, spectroscopy that come from CHARA, so from the Vega instrument at CHARA. So we are trying to get also further measurements and continue to model with the phonics model. So I just wanted to, I was interested to see your opinion on what would you like this and why exactly phonics, and where would you like this to go?
So when Emily and I were starting the Red Supergiant project back in the early 2000s, the MOGS models at that time did not go to a surface gravity of 0. They didn't go into they stopped at sort of the giant stage. And Bertrand Plez was kind enough to run models for use in this collaborative project that were at low enough surface gravities for the first time to be able to do this for real red supergiants. And my memory is that the Phoenix models actually go to log G of 0 now, because they understood people were interested in red supergiants. And one thing that's never been clear to me in this field is how much of what applies to AGB stars and red giants can actually be extended to red supergiants. That we're in, it seems to me that we're in such a different surface gravity regime that it's just like, I mean, I don't know the answer. I don't know the answer. And so it seems like all the results that we know about red supergiants, from effective temperatures to metallices and so on, are all based on this one set of very nice models that Bertrand ran. But shouldn't we look at some, you know, just see how reproducible this is? Is this, you know, are what we think limitations are due to 1D modeling, or are they due to MOGS? And I just think it would be, I mean, maybe someone has done this and I'm just not aware of it. That's entirely possible. But, you know, it seems like this would be a great summer student project for someone.
Yeah, great point. And I agree. Like, I also share your questions concerning this. So does somebody want to, oh, Marcus wants to comment perhaps on this. You should be able to talk.
Yes, we made a grid of Phoenix models for the work by then Arroyo Torres. And we haven't, I think we haven't compared to MARCS, but I don't believe that there's much of a difference actually. So it would be interesting to compare, but I don't think that there's much to be expected.
Yeah, so, okay, does anybody want to add on this on the phonics modeling? Or there is Ryan Iris that says that there also exist SATLAS models which could be used for red supergiants. It's a question. Yeah, in the meanwhile, if somebody wants to think about this, I would give back the word to Patricia that had something else that she wanted to say.
I just wanted to go back to this question of the mass loss prescription that theorists use. I know this is an area that Jako's worked on and produced various ideas that look perfectly reasonable to me, but why is it that the theorists go on using the Vasiliadis and Wood prescription for mass loss if they don't use the Reimer's prescription, when it's pretty clear all round that these things don't work particularly well? And what can the observers really do to try and get something more realistic out there for people to use? I guess I'm expecting an answer from the floor, as it were, one of the brilliant theorists or anyone.
People are encouraged to raise your hand or ping on.
Yeah, because I'm not going to answer that.
There's also Marcelo that has his hand up. I don't know if it's from before. Feel free to speak.
Oh, yes, indeed, it was related with this. So I think that the reason, I mean, I'm not using those mass prescription myself because I try to when I do the models, I try to use the ones that were like more supported by, let's say, observational or theoretical evidence. But I think that most people doing stellar evolution models, they stick to these Vasiliadis and Wood mostly because I mean, it has worked in the past, and still the observational evidence is not so much against it, I think, and so they prefer to stick to something that is compatible with their older models. I mean, that's the feeling I got from when discussing these things with other modelers. So.
Fair enough, but we ought to be able to do better now. We have much more data. We should be able to do better.
I completely agree. And in fact, I think that in particular for HEV stars, since all these theoretical models have started to produce like more reliable, I mean, working models for the winds of HEV stars, we have something which is much better, mostly because those which are based on observations and the mass loss, the problem is that the mass determinations or some of the parameter determination of the mass loss is very uncertain. On the other hand, I think that theoretical models are starting to do a much better job, and in particular, you can keep track of this difference between carbon-rich winds and oxygen-rich winds, which it seems to be quite different. So I completely agree. I think people should be changing, but I think that given that the observational evidence is not so much compelling, people sticking to their old prescriptions. I mean, that's the feeling I have, but of course I'm not using them, so maybe someone who is using them wants to defend them in a different way.
Andrea, do you want to add something? I see your hand.
Yeah, so before Andrea speaks, so I brought Andrea in. I just wanted to say that just because something was done 20, 30, 40 years ago or 50 years ago doesn't mean it's wrong or even that anything more recent than that is better. Just saying.
I wouldn't argue with that at
Andrea.
all, obviously, but there is a lot of observations since then and a lot more knowledge.
Okay, I just want to point out, not from 40 years ago, but just 11 years ago, that Xabi Mazzaros looked very carefully at red giants along the red giant branch in 3 globular clusters and very carefully modeled non-LTE expanding atmospheres, modeled the mass loss rates, and found that we were a factor of, I can't remember, 10 or 100 below Reimer's. And we're not the only ones who have found that. We've also measured directly using helium line very fast outflows at the escape velocity from red giants. No dust involved. It's coming from the chromosphere right there. We can measure it. So there's a lot of observational material and very sophisticated analysis and modeling from the radiative transfer point of view of these values. So it would be wonderful if someone would look at the papers and maybe give it a try, because clearly, I mean, the Reimers, it's always amazed me, the Reimers has this famous eta factor, and eta is your plaything, okay? And if you look at all the models, eta, the evolutionary calculations, eta has varied by, oh my gosh, factors of 100 maybe, but people still smile and put in a nice eta and move on, whereas there is other material, other results out there. So have fun. Thank you.
Andrea, you make a very good point. The reason why Rhymus is so popular is because it has a fudge factor, so you can always make it kind of work. And the same is true with the mixing length theory. It has a fudge factor, so you can always make it kind of work. I think that's the problem. So if you want to come up with some new prescription, make sure you build in a fudge factor.
Well, you can introduce the fudge factor. Call it beta, zeta, psi. Pick a number. Pick a letter. Okay, have fun.
Thank you, Andrea. And actually, there is a coming back to the discussion of before about the models. Phoenix, Ryan Norris also mentioned SATLAS. Joseph just said Comarc's models go out to log G -1. Joseph, I don't know if you want to talk about this more. And Marcus said about comparing different model atmospheres. There is a nice collection of 1D and 3D model atmospheres available, and he gave a link which could be useful to some of you. Marcus or Joseph, if you want to comment on this.
Yeah, maybe I mean the work that I put there, the link is a grid of model atmospheres. But I wanted to add something related to that. Marcus has shown that the atmospheres of red supergiants are also extended, so you cannot really reproduce them with a hydrostatic model atmosphere like the Comarc model. Not as much as the Mira stars, but they are more extended. And this extension means that the titanium oxide bands get stronger compared to a hydrostatic atmosphere. And that means that they look cooler than they really are. So maybe this explains the difference that was mentioned in the talk. But Marcus can give more details on that.
Marcus, do you want to add anything, or Phil?
I don't have anything to add really.
Okay, so I think we'll probably wrap this up because we could probably discuss for forever. So thanks very much, Patricia and Philip, for starting off this excellent discussion, and also bringing up more things during the discussion, and everybody who commented. Joya, do you want to say a few final words?
If you guys are finishing up now, could I just briefly say thank you to you both in public, as it were. You've done a magnificent job. It must have been a huge amount of effort. I've enjoyed it. My impression is that everybody else has enjoyed it. Thank you very much for everything. And I'm sure you're going to tell us what happens next, but thank you.
Thank you, Patricia, and yeah, thank you to all the participants, because it's really what made all the speakers and participants who made the discussion fantastic. And yeah, I just wanted to say to everybody, please feel free to go ahead and continue the discussion on Slack, on the general channel, on the all the channels. Promote your contributed talk. It's a place to continue this discussion. Also, we are working on a white paper to be produced. So we will need your contribution. Continuing the discussion is a way to, promoting further contribution that can go also in the white paper. And yeah, I just wanted to thank you very much again, you all, for taking part to this conference, and to all the amazing really contribution and discussions, which I really enjoyed and I learned a lot. And yeah, of course, also thanks to Jaco.
Thanks. Well, thanks to Joy. Just to say that our IE working group will be continuing under the leadership of Joya, who will take over officially from August, but she will take over as a chair. So I'm sure the working group will be very active, probably more active than when I was a chair. and hopefully we can bring the community together to work on projects that really require an interdisciplinary effort or a very large community support, which nowadays is sometimes important as well. Keep reading the AGB newsletter, which also deals with red supergiants. I would say this is one of the forums in which we can exchange ideas and make announcements as well. And Joya mentioned the white paper, so there will be versions going around, and you all have opportunities to both contribute and to just join it in support. So yes, thank you very much, everybody, and we wish you all well, and hope to see you sometime again in real life. Thanks.
Thank you all.